Welcome back. What I'd like to do next is to take a bird's eye view of sort of all of the things that we've been doing so far and go back to the beginning where we started talking about the example that we're using. Specifically, that we're looking at the relationship here between DES and the outcome, vaginal clear cell adenocarcinoma. And what we've done through all of these videos is we've shown how we can really evaluate that relationship between just those two variables. We can calculate an odds ratio between the risk factor and disease. We can calculate a chi-square to show the relationship between the risk factor and disease. But what if we want to also evaluate other variables as part of that relationship? So first of all, I want to take that description of what we're doing and turn that sentence into an equation. I think this might help a little bit as we're thinking about how we go about thinking about these other variables. So if our sentence is to evaluate whether the presence of DES is a predictor for VCAA, let me write that over here. We'll kind of come over here. I'm going to need a little more space. So this is written like we say things in English. What I'd like to do is convert that into a format that I know you've seen before. Basically, you've seen the math equation y equals mx plus b. But we're going to be converting this into a variation of that. And so we're going to be converting our presence of DES as a predictor of VCA into y equals b plus m times x. And you'll see why I did that in just a minute. So basically, we're taking the different variables and plugging them into the equation here. When we do statistics, we know our outcome variable and we know our predictor variable, and then we're trying to determine what equation represents the best relationship there. So y is our outcome, so that's VCCA, and I'll just keep some of these. So basically what we've done so far is we've shown that we can replace the x and the y variables in our equation with what we're actually studying. So if we're studying height and weight, or if we're studying cholesterol and heart disease, we can plug those kind of variables in. The other thing that happens along the way is that we still end up with these numeric variables. And what we do when we run our analysis is we find out what the relationship is, what our y-intercept is, what the slope that relates to that particular variable. So those are actually the unknowns in this case. And so we're just going to let them be because that's what our analysis will ultimately show us. The other thing that's really important to realize is that this linear relationship actually needs to be modified when our outcome variable is dichotomous. Remember how we had cases and controls? Well, that basically means disease yes and no. And when we have a yes-no variable, or cases and controls, or disease and well, or any kind of variable that dichotomizes, we actually need to modify this relationship just a little bit. And so what we end up having is that it's the probability of having that particular outcome, and then some expression of this particular numeric equation. And so what we're saying here is that DES is in some ways predicting whether a person has VCAA, but it's modified, and the actual equation is not important. It ends up being 1 over 1 minus e to the negative of this, and that's not particularly relevant, but what is relevant about that is that what that does is it allows the VCAA to be dichotomous. It allows it to be yes or no. And so that expression of the equation that we started out with then can allow us to see the actual relationship between our predictor variable and our outcome variable. Now, the magic of this happens when, let me get rid of some of these, when we erase that and we allow ourselves to add in more predictor variables. We need, in biostatistics, we generally call this beta 1. We add another numeric variable times, let's say, age. We add another variable for sex, or we have ways of adding things for race, ethnicity. And so what we end up with in this case is collectively, let me find another color, collectively, what is the impact of DES and age and sex on this outcome variable VCCA? And when we're doing this with logistic regression and we have this yes-no variable, we do have to make this modification where we use a slightly different equation for that, but essentially the idea is the same, where age and sex and DES are all collectively acting on VCAA together. So what this will help you do, even though we haven't learned specifically how to run logistic regression in SPSS, it'll allow you to see the kinds of research questions that can be answered by logistic regression. If, and we'll go back to our original, if all we're doing is looking at a single dichotomous variable predicting a single outcome variable, then probably the best statistical test is going to either be an odds ratio or a chi-square test of independence. But if we want to add on any other variables, 1 or 2 or 5 or however many other variables, either collectively we're looking at those variables together and their impact on the outcome variable, or we're still looking at that original variable's impact, but we want to correct for some confounders, then the best test is going to be called logistic regression. So that hopefully will help you understand a little bit more about where research can go with this. A lot of times in a basic statistics class, we'll learn the easier statistical tests and understand mathematically where they're coming from. Logistic regression is more complex, and it has a lot of different kinds of pitfalls to watch for, so you'd need to have some extra training in that goes beyond the scope of this class. But I do want you to be familiar with the whole notion of logistic regression, and specifically that the key feature is that the outcome variable is dichotomous. And so keep that in mind. We'll be learning about some other types of regression as we go through the remainder of this course. Thank you for joining me.